Right, good morning, and let's now start with some reminder or announcement for you. Your assignment number 1 is not going to be released this week, but it will be next week, as I mentioned in the calendar. So your best opportunity to really get prepared for it is to make sure you do the background study, right? We talked about many times about the basic recursion. So once we get to next week, when the assignment 1 has been released, everybody here will be assumed. You actually grasp the basic recursion. Background study, you can take that as mandatory if you don't really have the solid background about the basics, or optional if you're really confident. I'll leave the choice to you. But after next week, once the assignment 1 is released, I'll assume everybody's okay with the basic recursion. Of course, if you need help, reach out to me as early as you can. And last time, I found that maybe some of you may not feel so comfortable about the idea of callback value. The callback value, we did quite a bit of reviewed last time, but I think if you want to find a complete story and more example, I also included some references for you on the lecture site. If you go to the lecture site, I'll show you where you can find it. If you go to 2011 lecture site, you will see under week number 1 and 2, you can see there's some recommended study on callback value, about possibly half an hour or so. You can go over some other example. Right? That's also very basic, which we assume you actually learned from 2030. And if you look ahead, in your upcoming written test number 1, you can look up the calendar to see when it will happen. But written test 1 is definitely going to cover all the items you're assigned to actually study. Right? You can just want to get prepared along the way. Guys, any question so far? Are we okay? Right, so what I plan to do today, as I promised, I'm going to trace maybe the all-positive recursive method together with you, just to make sure you're okay with the tracing. And then I'll move on to a brand new lecture on the asymptotic analysis on algorithm. So we shouldn't take too long on the tracing, but I want to make sure it's properly done so you guys know what I expect from you later. Apart from that, do you guys have any question you want me to address regarding basic recursion? Anything? If you want, I don't mind spending some time. Anybody? Yes, go ahead.
So in one of your functions, I remember in the lecture, you used the helper function.
Yes.
Because in Java, without using a library, you can't put in a subarray. I'm not sure if you know what I'm
I see what you mean. I see what you mean.
So I was wondering if on a written test, because if you use the I think there's a util libraries where you can put arrays. Can we just use a library to do that?
Yeah, good question. I know exactly how to address your question. So the question was, let me rephrase that a little bit. Number 1, about maybe your written test or your programming test. And number 2 is about Java API. And number 3 is about using copies of subarray, right? Basically, all together. Okay. Right, I'll make it very clear to everybody. Okay. So number 1, in order to do recursion on array, of course, every time if you want to make a recursive call on a strictly smaller problem, you have to create some subarray. Of course, there are 2 ways to do it. Number 1, of course, you can use the Java API, of course. I believe something called arrays.copy, something like that. Okay, something like that. Number 2, you can use the approach that we cover in the lecture, meaning that you're going to have the from and to indices to see what range of elements in the array you want to look at. That's also something we talked about last time. Okay? Using the from and to indices, and of course, we are making use of call by value. In order to really do subarrays on the recursive call, you can do either way, in principle. And of course, API. And for your programming test and written test specifically, actually particularly for programming test, it will be forbidden to use any Java API to do recursion. Whenever you want to do recursion on the subarray, you have to use this approach. I want to tell you guys right at the front, you will not be allowed to use any Java library in the programming test. Everything you develop should be developed from scratch. Okay, I want to make it clear to everybody. Okay, so you have no surprise. Only allowed to develop items from scratch. And no Java library. For example, there might be certain exception methods which I will mention in that test or assignment explicitly. Other than that, you're not supposed to use. Otherwise, you might get some deduction on the marks. Okay, that was just the policy. Okay, and for your written test, you can assume that for questions I present to you, mostly they will be based on this particular flavor about using call by value and from and to indices. If I ever have to show to you maybe some Java API, I'll let you know in advance of the test so you can get prepared of reading code that uses Java API. Okay?
Java library is just a collection of Java APIs, or what's the difference between the APIs?
Okay, yeah. So whenever I say Java API, you know what that stands for, by the way? Yeah, application programming interface, very good. So whenever we talk about Java API, we're really referring to a collection of library classes, meaning that people have developed those classes. It has been accepted by the Java community, so you can use it if you want to. Beyond this course, whenever you develop any large-scale projects, the number one principle will be don't reinvent the wheel. However, in our little sandbox in this course, I really want you guys to know how to build things from scratch. That because you guys are still learning. So you really want to know how to build things from scratch before you can make use of other people's work. Okay? That's the policy for this course. I want to let you know. Okay? But if there's any more, once we're getting very closer to the programming test, I'll give you guys some study guide and also some example tests so you can see exactly what to expect. Right? Anything else you guys want me to clarify? Yes. Yeah. Are you more talking about written test or programming test? Okay, written test. Number one, for programming test, of course, it has to be valid Java. No question. Yeah, for written test, it depends on how the question asks. If the question say, you just sketch your idea in some programming syntax, in that way we can be more tolerant about missing semicolon and sometimes missing parentheses if it doesn't really change the meaning of your program. That's okay. On the other hand, if the question say explicitly you have to write in valid Java syntax, in that way it has to be valid. So it depends on how the question asks. You will be very clear in the context. Yeah, but you can say in principle we might be a little bit more tolerant in terms of the syntax you write in Java for the written test, maybe. Okay, I hope that answered your question. Yeah. Anything not clear, you can feel free to say, so everybody can benefit. Yeah. Yeah, so in that context there, of course, you will be forbidden to use any Java library classes, right? So that's a rule just before the test. So in the actual written test or in the programming test, if you ever have to write, let's say array does copy of, that would be considered as invalid, right? So you just make sure you don't do it. Everything should be built from scratch as we taught in the lecture. Okay, I see what you mean. Unless the question says you can assume there are certain methods that's available for you to use, unless you see that very explicit assumption. Otherwise, you cannot assume. Right? So the question itself will be very clear about the context you're working with. Very clear. Yeah. Well, you know, it's a fair game. We'll make it very clear to you what you should really expect in the test and during the test. And you guys will just have to answer accordingly. Okay. Yes, we're going to take one more, and then we should really move on. Go ahead, please. Yeah.
Function. I was a bit confused with respect to the base case there. So it says in the case of an empty array.
Yep. Yep.
But, oh wait.
That's okay. So you actually have some question regarding how to trace, maybe how to understand the code for all positive, right? That's something I'm about to cover anyway. Maybe that will address your question right away. Okay, good. All right. So guys, if you got more questions, ask me offline. If that's worth sharing class-wide, I'll do so as well as an announcement. Let's now move on very quickly to the all positive. If you remember what we said last time about the base cases, if you got an empty array, and we explain why it should be true, In this case, all the numbers are positive because you can find any example to show otherwise, right? You want to refer to the recording of that part. So it really depends on what the problem is. Sometimes for empty array, you may want to return true. And sometimes you may want to return false. It depends, all right? You want to really definitely review that part. And recursive case, that's something I want to show to you very quickly. And the idea would be we want to say the current element should be positive and the rest of the array, like a subproblem, itself should be all positive. We want to somehow combine these two results together. That's really corresponding to the principle of recursion that we talk about. So what I want to do is to show to you the code, the solution over here. And I'll try to be a little bit brief and concise, because if you want to find the full tracing, you can also find in the lecture. I'll try to see. Of course, if you want have question, interrupt me. We can spend more time. The way we do this is by this. You can say we got all positive over here. It takes as input an array of integer, just call A. And we're going to use call by value, meaning that we don't really create any new array objects along the way for various recursive call. All we do is passing the reference of A, right? That's the principle. We'll see that. We got another method over here. And one thing to note, if you look at this method here, it's so-called recursive helper method. Recursive helper method. Why is that recursive? You can see that this method here calls itself. So all positive helper, you can see it calls itself exactly over here. On the other hand, if you look at this method here, this method is not directly recursive because it calls just another method. Right? It doesn't call itself. So strictly speaking, this method is not recursive. It makes use of something else that's recursive. All right, let's clarify that first. Another design issue over here. Why do we need two methods over here? Why not just support this method specifically? I think one of you guys actually asked me offline after class last time. It's a great question. The main idea will be about user friendliness for using method. You want to think about if I just want to find out whether or not all the numbers in my input array are positive, should I be bothered passing 0 to the length minus 1? I shouldn't be bothered as a user. To really make your user happy, you want to make it as simple for them as possible. But for you as a programmer, you can do all kinds of tricks behind the scene, right? So typically, which I didn't really include in the context here, the method over here at this level here would be public. Let me write here. This one here would be public. On the other hand, this recursive helper method here would be private. So what's going to happen is this method here being private is only available behind the scene because it's private. On the other hand, when users want to use your method, this is the only one they can use. They can only pass their input array. How things will actually get manipulated over here is completely up to you as a programmer. Let's clarify that first. Go ahead.
So would this fall under the principle of abstraction?
You can think about abstraction. Yes, abstraction, put in its simple term. You want to get rid of information that's not necessary. So as far as the user is concerned, you have gotten rid of information like a from and to. So yes, indeed, it's like abstraction. Yes, that's good. That's good connection. I like that. Good. Alrighty, so let's now take a look. Let's look at the method here very quickly, and then we'll trace for a few inputs just to get some idea. So we call the recursive helper method here. You can see 0 and a.length minus 1. Let's look at this right away. 0, a.length minus 1. What does that mean? If you think about the array A, the input, right, A here. A will be a reference pointing to the beginning of some array. Could be empty, could be of size 1, could be of size very large. Doesn't matter. Let's say we go from 0 all the way to a.length minus 1, being the largest index, right? When we say we want to make a first call to this recursive helper method with 0 and a.length minus 1, what are we trying to say? We're trying to say conceptually we want to look at the entire array from index 0 all the way to a.length minus 1. That's typically what you have to pass as input to make the first call to the recursive helper method. Are we okay with that? Let's start with that. What's going to happen as I trace through the code is At every level of the recursive call, you're going to reduce the range of indices you have to really look at. So we're going to increase the value of from by plussing 1, right? That's something we're going to do. But we never try to create a brand new array. That's not something we are doing, okay? And let's take a look at the method itself, recursive helper method. So we got from here, and we got to here. We got 2 base cases. Okay, that may be what your question was about. Let's take a look. So there are 2 base cases. Let's see here. So these 2 are the 2 base cases. Okay. When from is larger than 2, it's really referring to empty array, empty range. We'll see that when we do the tracing. And from is exactly equal to 2. That means we are trying to talk about a range of just 1 elements. So these 2 are simple enough cases where we don't need any recursive call to solve the problem. Right? That's the principle. And otherwise, if we get to the 3rd case, when the size is strictly larger than 1, right? It's not 0, it's not 1. It could be 2, 3, 4, and onwards. In that way, we're going to do the following. We're going to combine 2 results using, right? You guys remember what the symbol is, right? Conjunction, right? We're going to conjoin 2 things. Number 1 will be the current elements being positive. The current elements being positive. And what about this part over here? We make a recursive call to itself. So that's why it's recursive. And then we are incrementing the value of from by 1. So that means we're reducing the range of indices to look at by 1. Okay? And this one is to make sure the rest of the array contains all positive. I'll try to visualize this once more just to give you a little bit more intuition. Let's say we got this array over here, A. What we want to check is, number 1, this first element over here is positive. Also, the rest of the array should be also positive. Whether or not this is positive is one Boolean. Whether or not this is positive is just another Boolean. We want to combine them using conjunction. That's exactly what we're doing, right? Conceptually. And this pattern here is so useful. You might just need that for many basic problems, right? Of course, when you solve the past lab number 5 from last term, you can definitely see that, right? That's something I rely on you to actually solve them by yourself. Reach out to me for questions. Any question about this fragment of code over here before I try to trace them? I'll trace it, with different cases. What you have to make sure right now is the big picture is clear to you. Maybe if there's some little detail you're not exactly sure, maybe try to figure out yourself. If no, come back to me. But make sure the big picture is clear and how you actually do this such code following the principle we talk about, right? Also call by value, right? All right. Let's now move on to trace 3 cases. The final case will be left as exercise for you. Okay, first case. Let's say the simplest case. If A is simply empty array, okay? So let me redraw that. So the A here is, simply pointing to an array where no elements are there. So let me just like that. It's not null, by the way. Empty array is different from null. It's not null. It's just that an array with no elements inside. And if you try to call all positive A, so you're basically calling this method here. In turn, it's going to call all positive helper with the same A over here. And then it's going to pass 0 and A.length minus 1. Guys, what's A.length minus 1 in this case? -1, right? Well, of course, hopefully it didn't just peak, right? So the idea would be A.length in this case would be 0, right? A.length in this case would just be 0, right? You can think about, I'll put it here again. A.length is equal to 0 in this case. So that's why you got 0 and -1, right? And when you actually try to look at this particular arguments, and when you try to trace the all positive helper, you got 0 and -1. Let me put it down. You got 0 and you got -1. You will see that you satisfy this base case right away because 0 larger than -1, I'm pretty sure you know it should be true. And then just return true. That's it. Right? So that will be the execution path for the very first one. That's it. That's a base case. So this shows that our little pattern over here definitely works for base case number 1 when the array is empty. You just have to make sure sometimes you may have to return true over here. Sometimes you may have to return false, depending on the nature of the problem. I'll take your question first. You have a question? You're fine.
The first case,
Yeah.
declared the array, we declared it as size 0.
Yes, exactly. So yes, for the first tracing case, very good. Let me clarify again. So for the first tracing here, we're assuming that we're passing an empty array into the call for all positive. We're going to see some different input values later. Yeah. Question?
I just want to make sure that that's the way you want us to draw to trace and to like draw the, because in I'm sorry, rough one. Because when I watched your videos, right, I believe your 2030 videos, you actually drew the stack trace, and what you did was at the bottom you drew.
Got it.
You wrote the functions that were called first, and then you wrote everything else on top.
Yes.
You don't like that. Yeah.
Got
So
it. Got it.
would that be part of the or no? Tracing.
I see what you mean. So in terms of tracing the recursion, there are two ways. Number one, it would be using a stack. So using a call stack to really trace recursion is the closest to what's actually happening here behind the scene. Because when Java runtime is executing your recursion, they use a stack to keep track. So that's why using a stack to trace recursion is something you must know to begin with. Okay, number one. And the example you got from the background lecture was the truth factorial. And also the Fibonacci number, right? So these were the two examples given to you. That will really give you some very clear idea how things should be done. Of course, if I give you a different method, you should really know how to do it. Number one, call stack. Another way to trace it would be when things get more and more complicated, using a call stack is still doable, but it may not achieve its goal for you to really see exactly how the method or algorithm will work. We'll see very clearly when I start tracing the more complicated input for the all positive. We'll see that. And another way is to use the so-called tree-like drawing. Pretty much like, so let's say a little bit look ahead. If I got this particular call, it's going to in turn cause this, and then it's going to in turn cause this. Eventually, we're going to get certain branching structure. That's what I meant by tree-like. We're going to see that in a moment, don't worry. And the second one is also something you should know, right? Both are possible. Of course, for the all positive, I'm only showing you the tree-like drawing. Should you also know how to trace user stack? Absolutely. You should know how to do it. That's something you can definitely try on the paper by yourself, and then if you want to check your drawing or your answer, come to me, and then I can go over that with you. Right? I hope that kind of addressed your question. Okay, good. All right. All right, guys, second tracing example. We'll do another, including this one, we'll do two more. Let's say we got another array, which is still very simple, but it's not really empty, but our A is an array of only a single elements. Let's take a look. So here we got A pointing to an array over here, only one element of index 0 for sure, and the element there is 4. Just that, okay? Conceptually, right? You know that the result should be true because the only element that's in the array is already positive. We know it should return true. That's what we expect to return from the method. But let's see if that's really the case. Let's try to trace it. So we'll first of all call all positive on the array A over here. And then in turn, it's actually going to call the helper method over here. And let's work out what from and 2 should be. According to here, it should be 0 and a.length minus 1. Agree? So 0 here is obvious, and this one here, you'll be a.length minus 1. A.length is 1. So a.length is 1. 1 minus 1, 0. That's how we work it out, 0. So in the case of 0 and 0, what's going to happen? Let's try to trace it a little bit further. Okay, so now we got 0 here and 0 over here. For the first condition, 0 larger than itself is false. Very good. What about 0 equals to itself? True. Agree? And then we're going to return a from larger than 0. A from, in this case, will be a at index 0. A at index 0 is 4. 4 larger than 0, true. So we return true. It's also a base case. We haven't dealt with any recursive call just yet. We don't need to. That's the convenience of having some base cases. Okay, so let me also highlight the execution path. We start with this, first of all, and then we try to check this condition by it's false. So we try to check this condition is true, so we're going to return. That's the execution path. Any question about the second case? All right. Third one. And I already drew some tree over here just for us to save some time. All right. But of course, that's something you really want to practice by yourself, draw from scratch. That's something I would suggest. Okay. I got some very nice whiteboard in my office. If you really want to do your exercise in front of me with my little bit supervision, come. And we can do it together. All right, so what we want to do now is A will be 1, 2, 3, 4, 4 elements, right? What's going to happen is A over here is going to be of index 0, 1, 2, and 3. And let's put down the element first. 4, 7, 3, and 9. Before I get down to the tree and the tracing, let's do a little bit of rehearsal visually. Okay? We know that to begin with, we're going to pass 0 and a.length minus 1. Effectively, it's going to say I want to look at from index 0 all the way to and including index 3. That's the initial one. The first recursive call is going to say I want to look at if this is positive and then the rest of the array is also positive, right? That one there effectively is going to look at this sub-range of the array. In order to complete this particular recursive call, what I need to do is look at if the first element here is positive, plus if the rest of the array is positive. That will be another recursive call, right? That one there, let me use maybe blue, let's say. That will actually look at this part over here. And in order to complete a recursive call on this subarray, it's still too large. It's not a base case just yet. So what we're going to do is look at if the first element here is positive, and then the rest of the array. In this case, it will be from and to will be just the same index, right? It's one of the base cases that we just talked about. That one there, let me use orange. So how many recursive calls will we have to make before we reach the base case? 3. Number 1, number 2, and number 3. It's a very important conceptual understanding you must have before we get down to the tracing, which itself will just correspond to this. Guys, any question? Yes, please.
I have a question for the base case 2.
Base case number 2, yes?
We just remove it, and let's say the recursive case would say return a from bigger than or equal 0.
Mm-hmm. Yes. So it's a good question here. Without diving too much into details over here, in some cases, not in all, in some cases, you might find that you don't necessarily need this particular base case where the array length is actually 1. You don't need to. But in some cases, you may have to. I don't really have any example on top of my head. So that's why I'm just including that anyway in the general pattern. So I would say you will be making the judgment. In your programming test, for example, if you really believe for the particular problem you're solving, you really don't need this particular base case, get rid of it. That's okay. at the risk that you might miss some boundary cases, of course. If you do believe you need it, keep it. But it doesn't hurt. Let's say even if this may not be necessary, but we're still including it, it's not going to cause your program to crash or to be incorrect. So that'll be my answer. Yeah, good.
Three recursive calls made.
Yes.
And you said that that's a concept that we need to understand.
Yes.
Concept, the amount of recursive
Yes.
calls.
Yeah. So initial call is to call the all positive with A. That's this initial call, which is going to pass the from and to be 0 to length minus 1. That's this green part over here. Okay? From there, we will need 3 recursive calls in total before we get to the base case. That's what I said you want to understand. But let's dive a little bit detail into it, and maybe you can ask some follow-up. How about that? Okay. All right, let's now get to a little bit different perspective to see how that works. Let's see. I want to do, first of all positive A. So I'm going to look at A over here. And then all positive helper is going to make a call to. And then hopefully you understand 0 here is corresponding to the 0 over here. 3 here is really corresponding to A dot length minus 1. What's A dot length? 1, 2, 3, 4. 4, right? That'll be 4 minus 1. So that's why you see 3 over here. Good so far? So far, no recursive call has been made just yet, but we will. And when we actually try to call this, it's going to call this with the first one is going to be 0 and then 3. All right? Effectively, we want to consider this range of elements in the array, the entire thing. And then the only branch is going to satisfy will be this. If you got 0 and 3, 0 larger than 3, false. So we don't really execute this part. And 0 equals to 3, also false. So we don't really go into this branch. So we got to go to this branch to make our first recursive call. Right? According to my diagram here, let me put pink over here. So what's going to happen is we're going to have A from larger than 0. From currently is actually 0. So that's why you see A 0 larger than 0, which will be 4 larger than 0. Together with the rest of the array over here. And what would that be? You can see A and then from plus 1, right? The from that we start with is 0. So 0 plus 1. And 2 over here remain the same. So that'll be from 1 to 3. You can see that's exactly from 1 to 3, the pink one, right? And then that one there is going to basically calculate this part over here, right? This will be itself a recursive call. And we're going to conjoin them together. So there will be some conjunction over here. Guys, are we okay? You guys haven't lost, right? I hope. It's okay to really get lost. To be honest with you, recursion is not a very easy subject. You just need repetition after repetition after repetition. I can give you guys maybe a little bit more tips maybe later about what's really the best way to learn about recursion. But for now, make sure you understand just the basic first before you can get more advanced. Okay? And let me just trace one more, and then we can finish the rest rather quickly. Okay? Now, this part over here is okay. This part here is rather easy. That will just give you true. And this part here, we don't know yet. Okay? So what we're going to do is we're going to execute this particular recursive call, which will boil down into. So what's going to happen is we're going to call all positive helper over here, right? And now the arguments will be 1 and 3. So it would be, you think about 1 and 3 over here. Right? We're calling the same method, but the argument values are different, 1 and 3. And would you guys be convinced we should really get to this part again? Right? Very quickly, 1 and 3. 1 larger than 3, false. 1 equal to 3, also false. Right? So once we get to this part over here, what's going to happen is A from will be A1, larger than 0. Right? So A1 larger than 0. So we are talking about this element here, 7. 7 larger than 0. And also the rest of the array, which will contain from index 2 to index 3. And if you look at this part over here, right, it's going to be what? This one here. And according to the color I used, it's going to be using blue, right? Currently, from is equal to 1. So here we're going to say 1 plus 1 for the from plus 1 part. And the 2 part is going to remain the same always, right? That's why you see 2 and 3 over here. All right? So effectively, we are really considering this part over here. All right? And of course, we're going to conjoin the result together. That'll be conjunction. Okay? Any questions so far? All right? We haven't reached the base case just yet. But for this one here, to trace this, let's get a little bit higher level. You already understand how to trace the code. I will encourage you to really complete that one, but let me go a little bit faster. In order to really do this tracing over here, you can see this is the from, and this is the to. So when you try to trace this one here, over here again, from and to, 2 and 3. 2 larger than 3, false. 2 equal to 3, false. So that's why you got to go for another level of recursion, where we should really increment this value 2 over here by 1. So that'll become 3. And the 2 over here remain the same. Right? That's how we figured it out. Okay? So what you will get is just another one. The from here is 2. So you want to check to see. Oh, let me be consistent. So I want to use orange. So this part over here is actually going to check to see 3. So A3 will be 3 larger than 0. And this part over here is going to restrict the range of indices just to the final bit, 3 and 3. Only the last one. That will be the base case, right? You can think about this part over here is reaching the base case, which means we don't have to grow the tree anymore. Base case. And what about this base case? So when 3 is equal to 3, right? That's something you can see. We only need to check to see whether A3 is larger than 0. It is. So this part here is going to give you true. And 3 larger than 0 here is also true, right? 7 larger than 0 is also true here. So now, conceptually, we're combining true, 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 and true, because every element here are true. So there are different aspects you really have to study on your own before you ask question. Number 1, how to program in Java. Number 2, how do you trace by using a stack. Number 3, how you can trace using a tree structure like this. You want to make sure every aspect is clear to you, given a recursive program. Any question? Please. Would I be expecting a particular way on tracing the recursion? I may. So maybe in the test, I might say, now trace this recursion using a call stack. Say trace it using a tree structure, I'll be very explicit. If I didn't make it explicit, you can use either way. Good question. All right, guys, 2 more, and then we got to move on. Please, go ahead, please.
It's like having a recursion in some problems. If there's like 2 recursive calls inside the same message. So you see how there's like 1 call here, right? Like how would Java reach the second recursive call? Because
yeah, for that question there, how about I deal with help you maybe offline? Because your other classmates don't have the context, so you might confuse them. I'll be more than happy to help you after class. Okay, please.
Using a call stack,
yes.
Test that might lead to some issues is that I noticed from your examples, and also I've done it in the past myself, it can get a little bit messy, especially if you don't have access to like several colors, if you're just using one pencil, you need to cross things out.
Yep. Yeah, I'll try to give you guys maybe one example. How about this? Let me give you this example on either Wednesday or maybe next Monday. I'll give you one where you can see how the written test question could be when I ask you call stack. Okay, that's a promise. I'll write it here, and then I'll come back to you either Wednesday or Monday. If I forgot, please remind me. Okay. Bring an example question on tracing via a stack. All right? If I really forgot, please remind me, because it's really definitely something I will expect you to do. Yes, question?
All of those calls that we made, and like each node in the tree, I guess, would each of them be an activation frame?
Yes, indeed. We actually talk about activation frame in the background lecture. You can think about every time when you are making a method call in this case, a node in the tree. You're basically creating a brand new activation frame, which contains the various information about this particular method call. For example, the name of the method, where the method comes from, certain class, and also what's the argument value, and etc. But you just need to understand that activation frame contains certain information that's necessary for you to understand what this call is about, just for that call. And then you will stack up, different activation frame as you go for nested helper call. Yes? Indeed. Yeah, so you can think about the call stack will just be a stack of activation frame. Every time you make a new call, you just got a stack on top. When you finish one, you got to pop it out from the stack, right? Alrighty, I think it's worth the time actually to really make sure at least you got hopefully motivated to really make sure you catch up with the basics. Starting from next Monday, I assume everybody's okay for the basics. If you are really struggling, talk to me now. Don't procrastinate. You'll be too late if you come to me 3 weeks later, all right? Okay, guys, why don't we, the next one is going to be about asymptotic analysis. Before we have a fresh start, why don't we take a short break and take attendance first, okay? Get your iClicker on your mobile phone ready, please. And I did a little bit of pre-processing so we can save time. I'm going to start a class now. And as soon as I start a class, let's take 1 minute for you guys to check in. All right? The idea will be, if you really find that you're having technical issue, you cannot really see the course or you cannot really check in, come right away to the podium. Come right away to the podium. And I have a sign-up sheet for you. Please. I'm going to start a class now. I hope your iPad's okay. Usually they're quite resilient. You should be fine. Oh, I do have a nice question for you guys. Give me a moment. If you have any trouble checking in, please come right away to the podium. Right away. Okay, it says like 1, right? Yes. Oh, just come. Just come. We don't have time to actually resolve it. Okay, come right away. All right, don't wait. Right away. Okay, just check in. Yeah, go ahead.
For the last one, when I logged in, it said 1 recorded assets, but I didn't do the thing, so I'm not sure.
Only for this time, just check in. Yeah, just click an option, please. Okay. All right, only 1, right? Okay, I'm going to stop the polling. Once I stop, please, no argument. If you got any issue, raise your hand. All right. Yes. Guys, thank you so much. It's now by my clock, 10:43. Why don't we take a break until 10:46-ish, 3 minutes. Don't go far. Yes. Okay, where are you? It's sorted by last name. Okay, that's you, right? Do you have your student card? Okay, thank you. If you don't mind, just as a formality. Thank you. Can you just please sign over here? Having trouble?
Yeah, I couldn't able to log in before.
Okay.
I didn't have this option to join the
Oh,
class.
now you seem to be, because I already closed. Okay.
I got it now.
Okay, how about, maybe for next time. Try to, I'll trust you this time. Next time, please launch earlier, okay, your iPad. It seems to be working.
I tried to do it another time too, but like I couldn't able to join the class. That I didn't get the link.
Okay,
I don't know, there was
okay.
a bug or something.
Maybe try to, you know what, you may want to use the app rather than logging into the website. Might be easier. Okay. Yeah, do you have a pen? I might have a pen. Yeah, just find your name first. It's sorted by last name.
Okay, it's okay. Yeah.
Okay, next time, yeah. Yeah, next time try to use it on a mobile app, okay, rather than just website. Yeah, can you sign here, please? Thank you. Okay,
Clicker didn't let me choose, so I just had no response.
Oh, because I already closed the poll. Next time, make sure you do that earlier. Yeah.
Okay.
Find your name over here, and then we'll let you sign. Sort it by last name,
Oh, by last name. Okay.
or maybe next page.
Yeah.
Okay.
Right there.
Yeah, if you can put a check mark and then sign, please. Thank you so much. Trouble? Yes.
The example of the tracing, if the array length was 4 and the first element was negative instead of positive.
Good question.
Yes.
That's something let me mention that very briefly
Okay.
in the lecture. Yeah.
Yeah, I was just gonna ask. Does the
Yeah.
recursion go on?
The short answer is no. It's not going to go on because the short circuit is actually going to make sure because if the first one is already negative over here, it's actually going to
The third if statement.
it's going to make sure this is already false. If this is already false, you don't really continue.
Yeah, but it returns false to the first one, right?
It will return false to the first one. Yeah. So no more recursion tree is going to be built because the short circuit, you're not going to go any further on this. Okay. Hi. Okay, next time come earlier, please. Okay, come earlier. Can you just find your name here and then sign? Okay, can you please put your signature here? Yeah, you just want to make sure next time when I say I start a poll, you want to go there right away by using the mobile app.
The app?
The app, there's an app for that. Okay, you can check the syllabus. There's an instruction there for you for you to use it. All right, thank you. All right, guys, let's now get started again. Yeah, so quick reminder, thank you so much for installing the app, but just make sure you don't really log into some website to really use iClicker. I think it might give you some trouble. Try to use the app that you can download to your iPad or mobile phone. And so we can avoid the trouble of having you sign up manually. All right, but we'll do this from time to time. Okay, we still have about 30 minutes or so. Let's see what we can do. We should really start a new lecture. Okay, oh, there's one more thing I want to mention. So, some very quick. There's another tracing over here for all positive, and for this one here, this will be your exercise. All right? And if you want to see the solution of tracing it, you can definitely go to the background lecture. I think that's one of the examples I went through over there. But we really did this in detail. You definitely want to do exercise on your own, too. All right? And let's now talk about a new lecture. That'll be more like an official start of the course, but we are addressing something very fundamental for you, so you wouldn't suffer later. We definitely need recursion substantially when we get to the tree topic after the reading week. So make sure you really catch up all the basics about recursion. And of course, assignment number 1 will also help you. Asymptotic analysis of algorithm. You guys may have already seen what asymptotic analysis is in your math class about big O notation. We'll review that, don't worry. But what's going to be new? And that'll be the essence for this course. We want to see how we can connect between math and also programming in this course. Whatever insights, mathematical proof, or mathematical property you actually learn from this asymptotic analysis, we're going to apply that to analyzing algorithm. Either one designed by yourself because you want to make a decision, or one that you have to choose between different alternatives. Right? That's something we'll see. And one thing we also assume that you actually know. That's something we will actually make sure you know by giving you the assignments. But if you want to catch up about using JUnit test, right? We're going to evaluate your programming test submission by using JUnit test cases. You got to make sure you know how to work with it. And there will be some Background study, again, optional if you feel confident about JUnit test cases. If you don't know what they are, I'm sorry, you have to catch up because that's something we have to assume you know from 2030. All right? So I listed exactly what you need to look at over here. If you want to check with me about whether you really understand them properly, again, drop by. And also, a general advice. In your assignments and programming tests, of course, for the assignment submission period, we're going to make some help available to you. So we can help you maybe sometimes debug the code. But a general tip, you want to rely more on the debugger, programming debugger. Can I just ask, don't be shy, any one of you who don't know how to use the programming debugger? That's okay, guys, don't worry, don't feel bad, right? I'm not trying to isolate you, so it's okay. Debugger is your best friend for finding errors in your code, okay? I can maybe try to give you guys maybe some demo, maybe quickly, maybe next time, just give you some idea. But this is what you have to do. Okay, for this one specifically, I will tell you what to do your self-study. And come to me if you got any question. Go to this tutorial over here, and let me see. You want to go to, okay, week number 2. Okay, let's see. Click on the link. Go to week number 2 over here, and then you will see how to really use a debugger. And if you look at part C over here, starting from here, it talks about how you can use a debugger. Because during the programming test, for me and the TA, we cannot really give you any hints whatsoever regarding if there's anything you get stuck on. We cannot. Even for the assignments, sometimes maybe you're struggling with certain code, but because you know your code the best. So by using a debugger is the best way to really debug the code. Use the debugger, and that's going to lead you a long way beyond the course. If you ask any professional software engineer, how do they debug their code? I can guarantee it's not about just printing statements to the console. That might be something it's a last resource survival guide, but debugger is the most professional way to do it. If you need help, come to me. Right? I'll be more than happy to walk you through some basic example. Debugger, so important. Okay? Cannot emphasize more. Okay, you got all the resources to you. All you got to do is spend the time and the efforts. That's all you got to do. Okay, learning outcomes about asymptotic analysis. For today, and also most of Wednesday, is going to be a little bit more mathematical. We have to make sure you guys recall the foundation. Okay? We assume you learned about this subject before, but I'm going to teach you from scratch. But ask me questions. And then maybe starting from the later part of Wednesday and also next Monday, we're going to see how we can apply the math into coding. That's the fun part. And we're going to really apply that thing throughout the course. Okay? And we're going to talk about algorithm and data structure, which we did in the introduction lecture anyway. And how do we measure how good an algorithm or just a Java method is? And how do we measure the efficiency of an algorithm? There are two different aspects of the efficiency, which I'll mention. And we want to see how we can measure using either experimental approach or theoretical approach. I'll briefly touch upon experimental approach. And we can discuss quickly about the pros and cons, and then we have to move on eventually to the theoretical measurement. Okay? And asymptotic analysis. That's the theoretical foundation you must have. And let's see over here. Yep. Later on, given any arbitrary two algorithm, we're going to say if the two are equally efficient asymptotically. What does that really mean? And when we say one is more efficient than the other asymptotically, what does it really mean? It doesn't make sense to you for now, that's okay. But we'll talk about it as we go, right? And also, given some algorithm, you want to determine its asymptotic upper bound. It's an upper bound in the asymptotic sense. That's also something you guys will have to know. All right, we're going to go step by step. Let's clarify some terminology here. Data structure, that's something we mentioned in the introductory lecture. Let's just revisit the definition. It's a systematic way to store and organize your data, so for accessor or mutators, basically. Right? And here is really important. Whenever we talk about some very fantastic, exciting data structure, there's no silver bullet. There's always pros and cons. There's got to be some limitation to certain data structure that we talk about. Especially a very common interview or exam question is to compare, for example, that's something you can just keep in mind. Arrays versus linked lists. These are the very common building blocks you have to use to really implement some data structure. And let me visualize quickly. You can think about if you're trying to build your own algorithm, your own algorithm, or let me say data structure, you're trying to build. And typically, you have two possible ways to go for. Either you go for the arrays approach, meaning that you have some private attribute of type array. You try to build everything accessor mutator of that particular data structure from scratch, right? That's one way. Another way is by using the linked lists. And we're going to cover two types of linked list. One is called singly linked list. The other one is called doubly linked list. That's something we'll cover after we talk about asymptotic analysis. And your job by the end of the course, of course, throughout the course, I should say, whenever you talk about certain data structure, we may simply ask you, is it more efficient to implement in array or in linked list? Or in the linked list case, is it more efficient to implement in singly linked list or doubly linked list? You have to say some yes or no, and then you got to give some justification in the mathematical rigorous way. All right? Let's go back. And for computational problem, basically every time you're given a certain problem telling you what the input should be and what the output should be is a computational problem. A very typical one is so-called a sorting problem. So if you are given some input sequence, right, let's say an array, what you really want to return is so-called permutation. I'm pretty sure you guys know what permutation is, right? Maybe from your math course. It's a rearrangement of all the elements. And for example, let's say this. You want to have certain algorithm or data structure, maybe certain input over here is something like, I have an array, let's say 3, 1, 4, minus 23, right? The output over here is going to be a permutation, meaning that I'm still going to keep all the elements there, but I'll arrange that from smallest to the largest. Minus 23, 1, 4, and 3, right? Input and output. That's just one example. Over here. It's a sorting problem. And let me give you also some look ahead. As a computer scientist or software engineer, you ought to know the following sorting mechanism before you graduate. Luckily, in this course, we talk about quite many of them. I think I'll try because I know it's important for you. Okay? Let me just list the name over here. Don't worry too much about how they work. They are fun to actually use, to really learn. Sorting. Insertion sort, selection sort, and merge sort, quick sort, finally, heap sort. You might be wondering, what about bubble sort? We don't talk about it in the course. Feel free to look for that if you want to. Yeah, if you are ever interested in why we are not talking about bubble sort, go to YouTube and simply search for Obama. You know the prior US president, Obama? Search for Obama and also bubble sort. You will see what I mean. Search for that, you will see. Okay, not now, please, not now. Yeah, maybe later after class, just for your own interest. He actually justified, well, actually, he didn't justify, but he tell you the guide about why bubble sort is not the way to go, okay? And it's more or less the order that we're gonna talk about the sorting. We'll talk about insertion sort and selection sort first, very soon. And then we'll talk about merge sort and quick sort. They will be the example for recursion part 2, most likely after the reading week, okay? And then heap sort will be the final sort we are gonna talk about. Heap sort is a very nice way. Itself is very, very simple to define. However, the underlying data structure the heap sort relies on called a heap, like a tree structure. That one there takes 3 or 4 lectures to explain. But it's worth learning for sure. Okay? And it depends on a data structure called heap. Right? We'll definitely try to cover every one of them. It's really good for you. And I think the best way for you to learn is to be able to, let's say, once you graduate from the course or the degree, number one, you should be able to describe each one of them in a very intuitive, conceptual way to a layman. That's what I will try to do when I first introduce the algorithm. Number two, you should be able to code it up yourself as well. For each one of them, for most of them, I'll give you the source code in Java. But of course, you can try to program that in a different way yourself too. Okay? And guess what? All these should be defined recursively. These two can be defined iteratively. All right? That's for your information. All of them will come. Okay? And then algorithm, yeah, it's going to be basically given a problem. You just want to specify a sequence of steps, different programming statement separated by semicolon, in the case of Java. Okay? And of course, any algorithm you want to really implement, you also need to justify which data structure you want to use. For example, array or linked list. You want to justify which one may be better asymptotically. All right? I want you to get used to this kind of expression. Whenever you say, my algorithm will be better than yours, but only in the asymptotic sense. Okay? Okay, how do we measure how good an algorithm is? Let's go over some basic concept. Correctness. I can tell you guys that's the number one priority. If your method or your algorithm is simply not correct, it doesn't matter how fast it can run. Doesn't matter. Okay? Does the algorithm produce the expected output, right? Given the input, it should really give you the correct output. You might say, oh, no, I got a constant time sorting algorithm, which is better than merge sort, quick sort, and also maybe a heap sort. But it only prints out hello world. That's why it's constant time. Is it useful? Absolutely not. I'm making some extreme example. My point is, correctness is always the most important factor. Throughout the lecture, usually correctness, you just want to remember that's the implicit first priority to achieve. But we will mostly be addressing the running time because that's more new to you. To really ensure correctness, one way to do it would be just to use JUnit test cases. You can come up with as many test cases as you like and make sure your algorithm pass on that between input and output. And the next one, assuming that correctness has been ensured, you got to ensure the next, efficiency. There are two aspects. Do you guys know which two aspects for efficiency? Efficiency in terms of, Faraz, go ahead. Space and time, very good. I'm pretty sure you guys have the same answer. Very good. Okay, let's go over that very quickly. Time complexity or efficiency. So that one is more about how much time does it take to really process your algorithm to execute it, right? But for the time complexity, I'll see how much I can go for, but just remember that will be something we'll focus on for this course. There's also about space efficiency. So memory space is not so much of a concern these days. You easily got 64 gigabytes of RAM, for your laptop, or maybe not to mention, some mainframe. So space is not so much of a concern. So we're going to focus more on the time complexity. Correctness, always priority. Efficiency, I just told you the answer. Let's not worry. Focus more on the time. Okay? Especially, I would just mention for you guys information. For this course, we are only talking about sequential execution. You basically execute one line at a time, from the top to the bottom. There is another paradigm of algorithm not even covered in 3101. That's only up to your maybe interest if you want to search on that. It's more like a concurrent algorithm, meaning that if you have different processors, if you try to distribute different tasks for the processors to really solve, in that way, how do you synchronize between the processors for the results? That's something much more complicated, but it's only for the more advanced learners. You don't need to worry. I just mentioned that for your information. Concurrent algorithm. I'll put it here. There are two actually. I'll mention both.
Is that similar to like parallel programming?
Yeah, like a parallel programming. Yeah, in some way, you need to really do parallel programming in order to implement concurrent algorithm. Yeah. Concurrent algorithm. And if you guys are taking 2031, you may actually learn about something called mutual exclusion or maybe semaphore, maybe later, not in the beginning of the semester. Just remember that term. That might be something you will see. That's more like a concurrent algorithm. Another paradigm is called distributed algorithm. Distributed algorithm. Concurrent algorithm simply means you got several tasks running at the same time. Distributed algorithm in a similar manner, but you're saying that you're trying to have geographically distributed locations. And somehow, each one of them is trying to come up with some computation result and try to synchronize between them. Very briefly. Okay? Not required by this course, but just for your knowledge. Okay, how do we measure the efficiency of an algorithm? So time, okay, so guys, take it for granted. Time is more of a concern than storage for this course, all right? And the solutions, put it very intuitively, your solution must be run as fast as possible. But here, when I say as fast as possible, what does it really mean? Does it mean it can take maybe 5 seconds, you'll be better than 10 seconds? Or something more formal, all right? That's something we'll address. And the running time usually depends on 2 input factors. Just give you some intuition. What could be the 2 input factors? Number 1, how large your input is. If you got an array of 10 elements versus 1 million elements, right? Also, the structure of your input. For example, let's say I want you to give me an algorithm to sort an array of elements. If I give you an array that's nearly sorted, almost sorted, it should be faster. If I give you an array that's barely sorted, it's basically completely out of order, that might take longer. That might kind of represent the worst case scenario for you, right? So these are the 2 bullet points you will see. So every time when we try to, later on, once we introduce to you about the mathematical analysis on algorithm, we always consider the worst case. You don't want to think about, I got case number 1, case number 2, and also all the way to case number 10. We don't really have to think about what's the worst case. Just plan for the worst. That's the simplest way to think about. But you don't really want to plan for the best case. Best case might occur, but not often. Okay? How do you determine the running time of an algorithm? There are 2 ways. Hopefully we can mention one today. That one should be rather fast to go over and give you guys some maybe remark. The first one will be like what you did in the physics lab or chemistry lab by experiments. When I say experiments, I really meant experiments. You just run the algorithm and use a timer to record how long it will take for the algorithm to complete. That's one way. Number 2 would be a much more rigorous and complete solution, which is by somehow formulating your running time itself as a mathematical function. I will address more precisely what this really means, and maybe a little bit later. I'll leave the bullet point number 2 for next time. Today, let's see if we can finish as much as possible for the first one. Okay? Any question? I saw some hands raised. So, you guys okay, right? Okay. First approach, how do we run by experiments? Assumption number 1, in order for you to run the algorithm, it better be executable, meaning that it should be implemented in some programming language, Java, Python, C#, whatever, right? You got many choices. And what we're going to do is we're going to execute the program on certain inputs. I'll give you an example. On certain inputs and maybe of different sizes, different structures, so you can compare the performances for as a wide range of input factor as possible. And this is the key. We want to somehow record the elapsed time for the algorithm. Starting from the beginning, I'm going to start the timer, and when the algorithm terminates, I'm going to stop the timer and see how much time has elapsed. As simple as that. You do have some Java library methods to help you on this. So for this part, you don't need to implement from scratch. Let me show you the code, which is rather straightforward. So here we say we got start time. We also got end time. The elapsed time will just be the end time minus start time. And what I put here in the middle is we're going to maybe have some method call to invoke your algorithm or method with certain input and see how much time it will take for that algorithm to really complete. Question?
Isn't there like dedicated tools for this? I believe it's called a profiler.
Maybe. There might be different way to do it. You can show it to me, maybe outside the class, if I can share with your classmates. But at least there will be one way, the most intuitive way to do it, which you can definitely run on your machine, right? Guys, are we okay with these lines of code? Should be rather straightforward, right? Okay, start time and end time, and calculate the elapsed time. As simple as that. I'm pretty sure the profiling mechanism you talk about should be along the line. Should be, I'll guess. Okay? And once you have done, you're going to visualize what's happening. I'll give you some analogy here, very briefly. For those of you who might be interested in doing machine learning, the idea would be usually when people do machine learning, they have to collect a huge amount of data. And then from those data, they will try to extrapolate certain patterns so that they can make prediction. So the idea would be you have to really summarize statistically from a huge amount of data to say, now if I'm going to have another event of a similar kind, what's going to be the predicted value? We're doing something kind of similar. You have to really rely on the results from the chosen data you have collected. Okay? Anyway, just some analogy. But let's take a look. Okay, you're going to visualize the result, and which we'll do for the example. Let's do one together. Okay? This one shouldn't take too long. I got about 8 minutes. Hopefully that's enough. Okay, let's say this. So the computational problem goes like this. The input is going to be a single character C. Any ASCII character you can type from your keyboard. For example, star. And then there's going to be some integer n, positive, let's assume. And then the output is going to be, you're going to repeat the character for that many of times. For example, if you pass the star 15, you're going to repeat the star for 15 times. Okay, sounds easy, right? And I will give you guys 2 potential algorithms or solutions to it. The first one is, I call repeat 1. Taking a character, taking some integer, I'm gonna somehow concatenate using plus equal. You guys know what that means, right, in Java. And I'm gonna concatenate to the answer for n times by the character. And then return the answer ultimately. That's 1. Algorithm number 1. Algorithm number 2. What I do is I still have the same parameter, character, and also n. I'm still going to run this many iterations, n times. But the way I'm going to accumulate the string, rather than having the plus operator in Java, I will use a library class called string builder. That one you can look into if you're interested. So string builder has a method called append. And I just want to keep appending to the end of the string, the character, for that many times. Intuitively, which one do you think is more efficient? Go ahead, please. The appending one? The second one, right? Yes? Why? Is there any judgment that you actually made? Adding to the end. Okay, that's a very nice intuition. Absolutely. Yes. So it turns out, you know what, guys, I tell you, it's interesting. That's why I definitely want to finish off this example today, make a remark, and then we can go on to mathematical analysis. Let me give you a little bit look ahead. I'm going to show you some statistics as a table. You might easily conclude algorithm number 2 is much more efficient than algorithm number 1. However, asymptotically speaking, they will be considered as efficient. That's something I want to mention to you first. What you think intuitively may not necessarily match what really is the case asymptotically. That's my point. But let's see. Maybe without showing you too much about how these two algorithms really work, let's just see which one might be more efficient based on the data, and then we'll see. Okay? Save some time. Okay, so here's a table. Okay? We're going to consider n would be how many times we want to repeat. And also repeat number 1 using the string concatenation plus operator. And also repeat 2 will be the append method, right? Let's say we start with n being equal to 50,000. For repeat 1, using string concatenation, it takes about 3,000 milliseconds. For repeat 2, only takes 1. From the external user point of view, it may not make a huge difference, right? It's actually still less than a second or so, right? It's not too bad. Now, I'm going to increase the size of n by doubling, okay? And I'm going to double the input size, you can see, from 50,000 to 100,000. From here to here, for repeat 1, it grows about 3 times-ish, right? This one here doesn't change, maybe just about 1 time. It seems to us, maybe repeat 2 will be the way to go, right? It seems to us. Let's double the input again. 200,000. From here to here for repeat 1, again, it grows about 5 times, roughly. And for repeat 2, oh, it does grow. It doesn't stay as constant, right? It will grow about 2 times. Hopefully you kind of see what I'm doing here. I'm trying to observe the pattern with my eyes from the table, okay? Go on like that. You can see we definitely got growing time over here, but this one still stayed pretty okay. So every time you double, you just grow about double as well, roughly. Finally, if you got this large input, it takes about 3 days for that, and 135 milliseconds for that. If you are interested in finding out if that's really 3 days, give it a try. Then to see that's really 3 days, maybe more, maybe less. Okay? I'm quoting this from some textbook, so I didn't really run the experiment myself, but it'd be more or less the case. Question? Yes. Yeah. Yes. Yes. Guys, let me give you a very quick idea about why repeat number 1 takes so much longer using concatenation operator. It's because, very quickly. Okay, we got about 3 minutes, but I think I can make a remark maybe next time. It's also a very good transition. Okay? And for this guy here, for the first one, okay? Think about this one here, answer plus equals C. Let's rewrite it a bit. Answer equals answer itself plus C. Right? Let's dive deeper into it. In order to really reassign answer to something new, we want to calculate this intermediate value first. That one there is going to make a brand new copy of answer plus some character. Imagine that if answer itself is already pretty big. Maybe answer is already some large enough string. So I'm just visualizing it as a string of character, let's say. What you got to do is, in order to calculate what to really reassign, you have to create a brand new string over here, intermediate, a temporary one on the memory. And then you're going to append this character over here to the end, maybe somehow, and then you're going to reassign that to here. So you got lots of intermediate object that will be created, which is going to occupy space, and somehow you're going to slow down your computer. That's really the insight into the problem. For append, it's basically just keep appending to certain objects, in which case it takes much less time. So this is an interesting example where the performance has been downgraded by the space requirements. Interesting example, okay? So the space inefficiency can imply downgraded or degraded runtime performance, running time, right? That's something we can learn. So guys, let me take just one more minute. I'm sorry about it, just 1 minute. I want to give you one little question to think about. Don't tell me the answer, think about it. Based on what we have got so far, input size is doubled, if you can see from the row, each row over here, and the rates of increase, roughly speaking. For repeat 1, every time you double the input size, it's going to increase about 5 times. For repeat number 2, it's about 2 times. Okay. Intuitively, you might decide to really choose repeat number 2. However, once we cover, starting from Wednesday, about asymptotic analysis, when you want to make a judgment about the algorithm running time, these two will be considered asymptotically equivalent in terms of their performance because they are both linear. That may not make much sense for you, but I want you to hear the sentence here. Watch the recording again if you want to. Really consider the sentence here a little bit, and we'll address that on Wednesday. Thank you so much. I'll see you on Wednesday. Please catch up with the recursion if you need to.